Alright students, welcome back. I hope you're all well under the current circumstances. It's been a very difficult time for all of us, but I believe we can make this work and continue the teaching and learning process. I've decided that I'm going to start recording my lectures and place them on either Ulink or YouTube. I've not made a decision yet as to what medium I'm going to use, depending on the data that it's going to take. So it will most probably be YouTube that I'll be posting it on. I'll also take the handwritten notes from my recordings and scan that in and place that on Ulink for students, just in case for students that don't have access to data currently. So the last time we met, we started talking about Section 2.3. We got about a third way through. What I'm going to do is I'm going to restart Section 2.3 and go through what we did in class and then move on from there. So for those of you that remember, Section 2.3 dealt mainly with properties of the determinant and Cramer's rule. I want you to go and revise Section 2.1 and 2.2 on your own, and I will try and have a tutorial lesson on a recorded lesson on Chapter 2 once we've done with this section. So in Section 2.3, I refer you back to the class notes. There we have our first determinant identity. If A is an n by n matrix and you take a scalar multiple of the matrix A, then that is the power of that scalar, and the power is indicated by the number of rows or columns multiplied by the determinant of A. And there's an example that illustrates how this identity is applied. Now I would just like, for interest's sake, to look at the derivation of this identity, because it's always nice to know where things come from as opposed to just learning them off by heart and applying them. Then also in general, we also established that the determinant doesn't distribute over the sum. Later in this chapter we'll see that it does distribute over the product of matrices, but generally not over the sum. And we can apply this identity we discussed above here to easily see why that's the case. If you take two matrices and you both set them equal to the 2 by 2 identity matrix, and then if you take the determinant of the sum of the two matrices, then applying that identity, we get that the determinant of 2 times the 2 by 2 identity matrix is simply 4 times the determinant of the identity matrix, the 2 by 2 one. And that we know already is 1, and that equates to 4. And then if we look at the sum of the two determinants separately, we know both have determinant 1, and if we add the 2, that becomes 2. So you can easily see that in general the determinant doesn't distribute over the sum. So I would just like to look at quickly at the derivation of this formula. And what we will be using is, we'll use induction on n. So let's quickly investigate that. Right, so let's quickly look at the derivation of that identity. So what we're claiming is we have the following claim. We claim that if A is an n by n matrix and K is some real number, then we have that the determinant of the scalar multiple of the matrix A is pretty much the nth power of the scalar multiplied by the determinant of A. So that's what we need to prove. Alright, so what we're going to do is let A be defined by this matrix here, 2, 1, 8, 2, 2. Okay, so what happens if n is 2? If n is 2, then the determinant of the scalar multiple of A is basically going to be the determinant of this matrix here. It's going to be the determinant of KA11, KA12, KA21, and KA22. And we know that's basically K squared multiplied by A1, A22 minus A12, A21. And that is the same as K squared multiplied by the determinant of A. Okay. So that establishes our base case. So this establishes our base case. This establishes our base case. So we're going to use the second principle of mathematical induction, stronger than the first principle. So we're going to assume that our claim holds for all m by n matrices B such that the dimensions of B is bigger than or equal to 2 but strictly less than n. Okay, so if B is a matrix that's a square matrix that's got fewer than n rows and columns, then this result holds. This claim holds. Okay, so we're going to look at that quickly. So that's our induction assumption. So now what we're going to do, what's the determinant of the scalar multiple of A? We can use the cofactor expansion. And to just recall, go back to in your notes and look at the cofactor expansion, the definition. So what we're going to do is, before we carry on, we're going to let Aij be the matrix obtained from A by deleting from A the ith row and jth column. Okay, that just defining that because it's just going to make my writing a little bit easier. So by the cofactor expansion, along the ith row, we obtain, okay, so what is the determinant of the scalar multiple of the matrix A? We know by the cofactor expansion. So what do? The cofactor expansion along the ith row, you keep the index I, you keep it constant, and you run through the sum of all your j, your indices j, which indicate the columns. Right, so what you're going to do is, what is the entry in the ith row and the jth column of the scalar multiple of A? It's basically the scalar multiple of this entry ij, the entry in the ith row in the jth column, and then you're going to multiply that with the cofactor of the entry in the ith row in the jth column. Okay, and you're going to sum over the j's. Okay, and we know this cofactor is the sine of that multiplied by the minor. And the minor is the matrix that you obtain from this matrix here by deleting the ith row in the jth column. And by our definition, that is going to be the determinant of which matrix? It's going to be the determinant of the matrix, the scalar multiple of this matrix here. Okay, and this matrix here we defined as the matrix obtained from A by deleting the ith row in the jth column. But deleting the ith row in the jth column of Ka is going to be the same as deleting the ith row in the jth column of A and then multiplying that resulting matrix with K. Alright, and now it just becomes a straightforward substitution. So basically what you're going to be left with is, you're going to be left with a sum. J runs from 1 to n. The scalar Aij, multiplied by Cij, which we know now is minus 1, I plus j, alright, multiplied by the determinant of the matrix Kij. And now this matrix here is a matrix that's got, firstly, this matrix here has got how many rows and columns? Well, it must have n minus 1 columns and n minus 1 rows, because how did I obtain this matrix? I deleted the ith row in the jth column. So therefore, just note that Aij is an n minus 1 by n minus 1 matrix, and so by our induction assumption, remember this rule is going to hold. This rule is going to hold. Okay? So by our induction assumption, what we're going to have is we're simply going to have that the determinant of K times the matrix Aij is going to be the nth minus 1 power of K multiplied by the determinant of the matrix Aij. Alright, so hence the determinant of Ka is then going to become this sum that we had there, K Aij minus 1 I plus j. And what is this determinant? We said it is K minus 1 multiplied by the determinant of Aij. And j runs from 1 up until n. Okay? And then replacing that, we have that is going to be j1n, k multiplied by kn minus 1 is kn. Okay, you're going to be left with Aij. You're going to be left with minus 1 to the power of I plus j. And that is going to be the determinant of Aij. Okay, and ladies and gentlemen, this is just the cofactor expansion of the matrix A along the ith row, and that you can just replace with the determinant of the matrix A. Okay, so that is where that identity comes from. So applying the second principle of mathematical induction. And it's a nice exercise to do because, again, it uses the cofactor expansion directly. Alright, so let's move on to the first theorem of section 2.3, which is theorem 2.3.1. Now this theorem gives a specific case where the determinant will distribute over the sum in this specific case, and that happens when you have three matrices A, B, and C, and they are all n by n, and A, B, and C are all the same except for the rth row. And we can obtain the rth row of C by adding the rth row of A to the rth row of B. And when that happens, the determinant of C is the sum of the determinant of A and the determinant of B. So if we have this special case, then the determinant will distribute over the sum. But remember, in general, it doesn't. So if you look at the last example on the page, you can see the matrix on the left-hand side and the two matrices on the right-hand side. They are all the same. They just differ in the third row. And you'll see the third row of the left-hand side matrix is the sum of the third rows of the matrices on the right-hand side. So in that case, then we can apply theorem 2.3.1 to calculate the determinant of the matrix C. So let's just investigate why it is that this determinant distributes in such a way using the cofactor expansion. Right, so let's quickly look at why that distribution of the determinant, how it works and why it is the case. So what we're going to do is we're going to define the matrix A as an n by n matrix. All right, so there we've got C11, C12, C1n, C21, C22, C2n. Right, so there you've got the rth row. And then you've got the row that comes just before the rth row, that you can still denote that by r minus 1, 1, CR minus 1, 2, so on and so forth, CR minus 1, n, and then you've got CR plus 1, 1, CR plus 1, 2, CR plus 1, n, and there you've got the nth row. All right, so we define the matrix A as that matrix there, and then you can define B as pretty much the same. The matrix B you can define as the entry in the ith row in the jth column of B is the same as A. When I is not equal to R, and the rth row is given by the entry otherwise. Okay. And then you can also define C as the matrix given as follows. The entry in the ith row in the jth column of C is simply, again, it's the same as A and B whenever we're not looking at the rth row, so it's going to be Cij if I is not equal to R, and it's pretty much going to be the sum of the rth row of A and the rth row of B, so that's pretty much going to be then ARJ plus BRJ otherwise. Okay, so there we've got our definition of the respective matrices. So now determining the determinant of C, we can expand along the rth row. So expansion along the rth row is simply that will give me the determinant of C, and the determinant of C is going to be this cofactor expansion. So you're going to sum over the indices j from 1 up until n. You're going to look at the entry in the rth row in j's column of C, which in this case is that quantity there. All right, and you're going to multiply that with the cofactor. The cofactor of the entry in the rth row in the j's column. Recall that, just remember that this cofactor is given by the sign, that sign multiplied by the minor. Right, now the minor is what? The minor is the determinant of the matrix that I get by taking C and cancelling the rth row in the j's column. Now if I go back to my original matrix and I cancel the rth row in the j's column, so there I cancel the rth row in the j's column. So if I take C and I cancel the rth row in the j's column, I'm pretty much left with there. If I cancel the rth row in the j's column lies somewhere there. That resulting matrix is going to be the same as the matrix that I get by taking B and cancelling the rth row in the j's column of B. And that's going to be the same as the matrix that I get by cancelling the rth row in the j's column of C. So just looking at that, we will have that this will become that multiplied by the determinant of the matrix ARJ. Now remember from the previous example I defined ARJ as the matrix that I get by cancelling the rth row in the j's column. Okay, and that you can replace as well by the determinant of BRJ. And BRJ I'm defining as the matrix that I get from B by cancelling the rth row in the j's column of B. Right, and these two determinants are the same because of the way A and B is defined. Cancelling the rth row of A in the j's column of A and cancelling the rth row of B in the j's column of B, that is going to result in exactly the same matrix. So hence, to conclude, using the cofactor expansion, the determinant of C then becomes the sum in, right, plus the sum of that. Okay, and we can do this replacement that I have there. You can replace CRJ pretty much by this value there. Okay, and then again you can do the same here. That is BRJ, and again you can replace it with that minus 1 R plus J multiplied by the determinant of BRJ. All right, and then what is this? This is the minor with respect to the matrix A. So again, you can, what is this? Essentially, this is the cofactor expansion of the matrix A along the rth row, and that will just give me the determinant of A. And essentially this, again, this is the cofactor expansion of the matrix B along the rth row, and that again is just the determinant of B. All right, so that is a quick illustration of why this distributive law holds when A and B is specifically defined in terms of C. So that's not a very difficult to show this, but it's also a nice exercise to do this using the cofactor expansion. All right, so next we discuss lemma 2.3.2. So lemmas are normally results in mathematics that on their own they're not particularly interesting, but they are used to prove more fundamental results. So our aim in this section is to prove that the determinant does in fact distribute over a product of matrices. And for us to do that, let's consider a special case. Let's look at the product of an elementary matrix with another matrix, and then see how the determinant behaves over that particular product. So lemma 2.3.2 just states that if B and E are two n by n matrices and E is an elementary matrix, then the determinant distributes over the product of an elementary matrix with the matrix B. And then also you can, generally this law holds for a sequence of elementary matrix. If you take a sequence of elementary matrices and you take the product of that sequence and you take the product of that whole sequence with another matrix B, then the determinant distributes over that whole product in the way illustrated here in the last two lines of this page. So let's quickly go and investigate why it is the case that the determinant behaves this way, because that'll enable us to prove one of the main results of this, one of the main properties of a determinant. All right, so let's check why the determinant distributes over a product between an elementary matrix and another matrix. So what we want to do here is we claim that if E and B are two n by n matrices, such that E is elementary, then the determinant of EB is the same as the determinant of E multiplied by the determinant of B. All right. So to prove this, we need to go back to our previous theorems in section 2.1 and 2.2. So I urge you to go and revise those theorems. So we're just going to apply it here. So we need to consider three cases. Remember, an elementary matrix is a matrix obtained from an identity matrix by doing one of three things to the identity matrix. The first one is interchanging two rows of the identity matrix. The second one is adding a multiple of one row to another row. And that's the second part. And the other way of getting an elementary matrix is multiplying a row of an identity matrix with a scalar C. So we need to consider three cases. So what we do is we consider three cases. All right, so the first case is you obtain E is obtained from the n by n identity matrix by interchanging two rows. Okay. Then, if you look at the determinant of EB, now, there's a law that states that if you take a product of an elementary matrix with another matrix, what you essentially do to calculate that product is you can do it easily. All you do is you take the operation you use to get E from I, and you simply apply it to B. So how did we get E? We interchange two rows of I. So you're going to calculate the product by interchanging two rows of B. And there's a law that states that if you interchange two rows of a matrix, the determinant of the new matrix is negative the determinant of the old matrix, which in this case is B. We know that we can replace -1 with the determinant of the elementary matrix, because the determinant of an elementary matrix that I obtained from interchanging two rows of the identity matrix is simply -1. Okay, that's from previous knowledge. So we know in this case this law holds. So the second case is E is obtained from IN by multiplying a row of IN with a scalar C. Right, so in this case, this is the second case. In this case, the determinant of EB. Okay, now you have to go and think again. How did we get from I to E? Is you multiplied a row of I with a scalar C. Now there's a law that, remember, how do we multiply E with B? Whatever you did to get E, you do to B. So you multiply B with the row of B with a scalar C. Now there's a law that states that the determinant of a matrix that you get by multiplying a row by a scalar C is going to be the determinant of the new matrix is going to be C times the determinant of the old matrix, which in this case is B. Because EB is the new matrix, B is the old matrix. And we can simply replace C with the determinant of E, because E is going to be a upper triangular matrix. And we know what the determinant of an upper triangular matrix is. It's going to be C in this case. And then the last case is E is obtained. E is obtained from IN by adding a multiple of one row to another. And again, it's the application of our previous theorems. So again, how do we calculate the determinant of this matrix? The product of this, you obtain that by applying the operation you use to get E to B. So what are you doing? You're taking B and you adding a multiple of one row to another. Now, according to a previous theorem from section 2.1 and 2.2, the matrix that you get by adding a multiple of one row to another, the determinant of that matrix is going to be the same as the determinant of the old matrix. So the old matrix is B, and EB is the new matrix. And that matrix we obtain by multiplying one row with a scalar and then adding that to another row. So the determinant stays the same. So we can replace that 1 there. We can replace that by the determinant of E. Okay, because the determinant of E, the matrix that I get from I by adding a multiple of one row to another, it is again going to be an upper or a lower triangular matrix, and again the diagonal entries, you take the diagonal entries and you multiply them together, and that's going to give you the determinant, and that's just going to be 1. All right, so that clearly proves this claim. Now we can, just a note, we can actually apply this rule recursively and find a more general expression. So if this is a sequence of elementary matrices, all right, then if you were to calculate the determinant of the product between all of these matrices with B, right, then we can apply this claim recursively. So you can basically write that as this product here, and apply your law. Okay, so the above claim specifically states that we can do this. Okay, multiplied by the determinant of all right, and then again you can group E2 with the remaining part of the product, and you can pretty much again just write this out, again apply your law to this product there, and you see that that is the determinant multiplied by the determinant of E3 ERB. Okay, and again you can apply this rule recursively like I stated, and you can then in general prove that this is the case. Okay, so we see a pattern emerging here that you can distribute the determinant over a product of an elementary matrix with another matrix. So now the question is, can we extend this rule? Can we prove a stronger result? In other words, does the determinant distribute over a general product of square matrices? And this is what we're going to establish next. And yes, in fact, it turns out that you can distribute the determinant over a product of matrices. All right, so before we can establish one of our main results in section 2.3, we have to look at at theorem 2.3.3. And theorem 2.3.3 gives us a relationship between the invertibility of a matrix and its determinant. Now you have two mathematical statements. A is invertible and the determinant of A is not 0. And those two statements are mathematically equivalent. So remember, that means that you cannot have one without the other. The A will be invertible only when the determinant of A is not 0. Okay, now to prove this, we take R to be the reduced row echelon form of A. And remember that we can find a sequence of elementary matrices that we can successively apply to A, and that will eventually lead to its reduced row echelon form. Remember, each elementary matrix is obtained using exactly one row operation on the identity matrix. Now, applying the successive product to A is equivalent to to applying a row reduction successively. So then we can take the determinant on both sides and again use our previous lemma, lemma 2.3.2, to show that that determinant distributes over the product. And we have that the left-hand side is equal to the right-hand side. Remember I said it recursively, you can apply lemma 2.3.2. So on the left-hand side, you've got the determinant of the products being equal to the determinant of the reduced row echelon form of A. Now note that the determinant of an elementary matrix is never 0. So that will imply that what you have on the left-hand side, if that is not 0, then the right-hand side will not be 0. In other words, because the determinants of the elementary matrices are non-zero, it means the only way the left-hand side can be 0 is that if the determinant of A is 0. And the only way the left-hand side is not 0 is if the determinant of A is not 0. So therefore, the determinant of A is not 0 if and only if the determinant of R is not 0. Okay, so if the determinant of A is not 0, it implies the determinant of R is not 0, and vice versa. If the determinant of R is not 0, then it implies that the determinant of A is not 0. So we can now prove this theorem. Therefore, if A is invertible, then the equivalence theorem, remember the equivalence theorem states that the reduced row echelon form of the matrix A is the identity matrix. And therefore, the identity matrix, the determinant of the identity matrix is 1. And that's going to lead to a non-zero determinant for R on the right-hand side. So on the right-hand side, you've got a non-zero quantity, and on the left-hand side, you must also have a non-zero quantity which will force the determinant of A to be not 0. So that's proving from left to right. So now proving from right to left, we'd assume that the determinant of A is not 0. Now if the determinant of A is not 0, it means this product on the left-hand side is not going to be going to be non-zero. And that's then going to imply that the determinant of R is not going to be 0. Now, the determinant of R, the fact that it is not 0, is going to force this R to be a matrix that's got no 0 rows. And because the reduced row echelon form doesn't have a row of zeros, it's going to force the reduced row echelon form to be the identity matrix. Because remember, the reduced row echelon form of a matrix can be one of two things. It's either the identity matrix, or it's a matrix that's going to have at least one row of zeros. So it's either one of the two. If a reduced row echelon form doesn't have a row of zeros, it's going to force that reduced row echelon form to be the identity matrix. And because the reduced row echelon form of A is an identity matrix, it's going to force A to be invertible by the equivalence theorem.